So our main topic today is limits and continuity. But as a warm-up for that, we're going to graph this rational function. So you worked on that right now. Let's work through it now together. First thing you want to do in this kind of context is, well, like we talked about last time, if you got like quadratics or cubics on the top and the bottom, you'd want to factor if possible, and then cancel any common factors. Well, we don't have to do that here because we just have two linear factors. There's nothing to do as far as factoring goes. And there's no common factor. You can't cancel the 2x minus 5 with the x plus 3. So that's already done. Second step is to try to find intercepts. For the y-intercept, plug in x equals 0. The y-intercept is where it crosses the vertical y-axis. That's where x is 0. We plug in x equals 0 and see what we get. You'll get negative 5 over 3, which is, yes, negative 5/3, and you can write that number in either way. You can put the negative sign up there, down there, or out in front. It doesn't matter. But negative 1.67 if you approximate it. Okay? What about the x-intercept? That's where the numerator is 0, as long as you canceled any common factors. Set f of x equal to 0 and solve for x. The only way a fraction is 0 is if the top is 0. Though again, if the top and the bottom are 0 at the same time, that could be a, it's possible it can be a vertical asymptote. It's also possible it could just be a hole in the graph. It depends on the situation. That's going to imply that the top is 0, 2x minus 5 is 0, which means 2x equals 5, which means x is 5/2. Word of warning about solving equations like this. When you're doing this process, you're really only finding possible x-intercepts, possible roots in this case. To truly verify that it's an x-intercept, you really need to plug it into the function to confirm you get 0, but that's easy. It definitely happens in simple examples like this. But there are some situations where in the solving, you actually get what are called extraneous roots that don't work in the original equation. Maybe we'll do an example of that some other day, not today. So the x-intercept will be 5/2, which is 2.5. Next, you should look for asymptotes. Vertical asymptote. Vertical asymptote. Here's how you spell asymptote, by the way. Ignore that little dot up there. Asymptot. I think I spelled that right. Looks right. Vertical asymptote is where the bottom is 0 as long as the top is not 0 at the same time, typically. Again, since there were no common factors to cancel, that will happen here. X plus 3 being 0 means x is negative 3. There is a vertical asymptote at negative 3. Doing all this before I plot any points, well, I guess I am plotting 1 point effectively. X is 0, y is negative 1.67. But other than that, I'm not plotting any points. Does it have horizontal asymptotes? Not always. Rational functions don't always have horizontal asymptotes. They do if the degree, the highest power of the top, is less than or equal to the bottom's degree. In this case, they're equal. They're both 1. That's the highest power of x. And in fact, because of that, this is something you can take to the bank. When the highest power and the top and the bottom are the same, the vertical or the horizontal asymptote will occur at the value of y that is the ratio of the coefficients of those highest powers. 2 divided by, well, there's a 1 there. Horizontal asymptote occurs at y equals 2 divided by 1 is 2. Again, that only applies when the degree of the top and the bottom are the same. In this case, again, those highest powers are both a 1. If they were both a 2, it would still apply. If they were both a 3, it would still apply. And in all those cases, you look at the coefficients of the highest power. If you didn't see a coefficient, again, that means it's a 1, really. And so that ratio, 2 divided by 1, which is 2, is the location in the y coordinate of the horizontal asymptote for this function. Okay. If the degree of the top is smaller than the degree of the bottom, like if that were a 1 and that were a 2 there, then there would be a horizontal asymptote at y equals 0, the x-axis. We'll talk about y in a little bit here. And if the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptotes. Question? So this doesn't... I just summarized what happens. If the degree of the top and the bottom are the same, look at the coefficients of the highest power like I did here. If the degree of the top is smaller than the degree of the bottom, there's still a horizontal asymptote at y equals 0, the x-axis. And if the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. If it's 1 higher, if that's a 2 and that's a 1, there's actually going to be a slanted asymptote. We'll try an example of that, but not right now. So, taking all this information, we can start to get a good feel for what the graph might look like without even plotting many points. I guess that there's a second point I've effectively plotted. When x is 5/2, y is 0 as well. Let's go ahead and mark those. The y-intercept is at -5/3. There's -1, there's -2, there's -3. -5/3 would be right about there. The x-intercept is at 2.5. Here's 1, here's 2, here's 3, right about there. Vertical asymptote at x equals -3. That's a vertical line. Here's 1, -1, -2, -3, right about here. Horizontal asymptote at y equals 2. Based on these data that we have here, the points and the asymptotes, what is the most likely picture of the graph of this function? Most likely, based on experience, I know it's probably going to do this. Just watch my pen. I'm not going to actually draw it. It's probably going to go up like this over there. And over here, it's probably going to go like that. To be sure, plotting points helps, but also thinking about limits as x approaches, in particular, -3, either from the left or from the right. Is that your question?
I was going to ask, like, what is the other possibility for it?
Well, you might wonder if it maybe crosses the horizontal asymptote before coming back down toward it. With this simple example, it probably won't. That's the kind of thing you might wonder about.
All right.
You might also wonder, instead of coming down like that over here, could it possibly come up like that? With this kind of simple example, it won't, but there are some situations where it's a little bit more complicated where it can.
All right.
Let's plot a few more points. For example, what's f of -1? Here again is the formula for f. I'll rewrite it down here. F of x is 2x minus 5 over x plus 3. F of -1 would be then plug in x equals -1, -2 minus 5 over -1 plus 3. Double check that I don't make a mistake. I think that looks okay. That's -7 over +2. -3.5 seems reasonable. Yeah, -3.5 down around there. Let me find f of +1. Should be somewhere in the ballpark of -1, I'm guessing. Plug it in there, get 2 minus 5 over 1 plus 3. -3 divided by 4, -0.75, not too far from -1. Right around here. F of 2 should be maybe -0.25 or something. 2 times 2 is 4, minus 5 over 4 plus 3, -1/7. Not such a nice number. About -0.14, I believe. F of 3 should be slightly positive, maybe in the ballpark of +1/7. F of 3 going up here should be 6 minus 5 over 6, +1/6. Doesn't look like it's going to go toward that horizontal asymptote very fast, does it? Okay, well, that's just the way it is, I guess. It will. We know this is going to be a horizontal asymptote, or you're trusting me at least. What about it back over here, f of -4, for example? Is it going to be up high like I'm guessing? Let's try it. Plug in -4 here, get -8 minus 5 over -4 plus 3. -13 over -1 is +13 off the scale. It's way up here. F of 5, or -5, excuse me, should be smaller because we're going further to the left. If the graph is coming down as we go to the left. -5 gives you -10 minus 5 over -5 plus 3, -15 over -2. +15 halves, which is +7.5. It is smaller. Okay, effectively, it's way up here. That kind of thing. I'm not trying to take the time to make it super accurate from this point on here. This seems to be what's going on. Can we do limit calculations? Another question?
Would that be reflected over on,
Translated up? Possibly. Yep.
All right.
Possibly could be a reflection across y equals x here. If I had to guess, is it? I'm guessing actually probably not. Maybe because the coefficients of the x's are different. Maybe not. But that's a good guess. That's a good hypothesis and something you could conceivably try to check. How about some limit calculations? What's the limit of this function f of x? For example, as x approaches -3 from the right. That negative sign means this is the number -3. The plus sign to the right of it means I'm letting x approach it from the right. Not through positive values. From the right is what that plus sign means. Like getting close to -3. Right in here, like -2, -2.5, -2.99, -2.999. I'm letting x get closer and closer to -3 from the right, but not equal -3 because the function would be undefined there. Is it possible to figure out what this limit is? Well, yes and no. Why no? Well, the reason it's not possible to find this limit is because the limit's not a number. But yes, it is possible to find this limit because it's either plus or minus infinity. I know that's confusing. What do I mean? I've said this already. Infinity in this class and minus infinity are not numbers. But when you write them in these kinds of equations, they do represent ideas. In this case, the idea, it seems like from the evidence here, of going down forever and ever. Getting below any horizontal line, no matter how low it is, by getting close enough to -3 without actually equaling. Can that be reasoned out just by looking at the formula? Yeah. Imagine plugging in a number really close to -3, barely to the right of it, like -2.999. -2.999 plus 3 is a really small positive number. Yeah, 0.001. -2.9 times 2 minus 5 is negative, and not so close to 0. A negative number, not very close to 0, divided by a very small positive number is a very large, quote unquote, negative number, way down there. Now, that's not a proof that this is minus infinity, but it is an indication that it seems like that's probably true. To prove it, a little too advanced. Okay. Actually, we will try to do proofs like that, but not today. But for simpler examples. Maybe on Friday. Okay. So I'm writing equals minus infinity, but this does not mean that minus infinity is a number. It's just shorthand notation to say this graph's going down forever and ever. It gets below any horizontal line if I make x close enough to -3 without actually equaling -3. Another question? Thank you. You're telling me what the numerator is there? Okay, yep. So yes, it's a very large negative number divided by a positive number very close to zero.
The answer.
Oh, for the whole thing? Okay, thanks. How about if we approach -3 from the left? You see two negative signs here. The first negative means this is -3. The second negative does not mean negative number, but in this case, they happen to be. It means you're approaching -3 from the left. These are called one-sided limits. You're approaching either from the right or from the left. Once again, it seems from the graphical evidence as we approach -3 from the left, the outputs are getting really high, going to plus infinity. Yes, that is correct. Can that be reasoned out? Once again, you can think about plugging in a number close to -3, but not equal to it, but this time less than -3, like -3.01. Going to give me a big negative number up here and a small negative number there, close to 0, like -0.01. Right? -3.01 plus 3 is -0.01. Big negative divided by small negative is big positive. Again, this is fuzzy math, hand wavy math. When I say that kind of thing, I didn't prove anything, but I hope it seems reasonable. And the closer you get to -3 without actually equaling it, the higher the value of this function is going to go. It does go to plus infinity. It's going to get above any horizontal line no matter how high, as long as I make x close enough to -3 without actually equaling it. What about the horizontal asymptotes? Can I really prove that the horizontal asymptote, I shouldn't have said totes, I should have said asymptote, single horizontal asymptote. Can I prove this is the horizontal asymptote without just relying on my calculator? And by the way, if you did make this with your calculator, that's fine, but you should be able to draw it by hand as well. Yes and no. Okay, yes, we can, but we got to be careful about it. Can I compute the limit as x goes to, say, plus or minus infinity of this function? And will the answer be 2? The horizontal asymptote. The answer is yes, but you got to do it in the right way. And the calculation for this kind of example is the same whether you let x go to plus infinity or minus infinity, meaning whether you let x go forever and ever to the right or forever and ever to the left. For rational functions, when they have horizontal asymptotes, this limit's going to be the same either way. For the arctangent function, inverse tangent function from last time, they were different, right? There was 2 distinct horizontal asymptotes. -π/2 as x goes to minus infinity, and +π/2 as x goes to plus infinity. Functions can have 2 distinct horizontal asymptotes, but when these rational functions do have horizontal asymptote, it's just a single one. So what do? You just plug infinity? Do you get 2 times infinity minus 5 over infinity plus 3? No, don't do that. Oh, so many confusing things. Except we will kind of do that when we talk about something called L'Hopital's rule later in the semester. But that's not now. So many subtleties. It's the way it is. That's part of what makes calculus difficult. And there's all these different things to think about. Now, don't do that. Instead, when you got this kind of situation, you do a little trick. Before you let x go to plus or minus infinity, you need to multiply the top and the bottom of this fraction by the same thing so that it doesn't change the value of the fraction. And that same thing is 1 over the highest power of x. Whatever the highest power of x is, in this case 1, on the top and the bottom, multiply by 1 over that highest power of x. Why? It's mysterious at the moment. It's a trick. How do people come up with math tricks? through experimentation, trial and error, that's how. Sometimes over many, many years. And that person who struggled with this problem 300 years ago for many, many years, well, now I can just tell you what to do in 5 minutes. Okay. It probably didn't take them years. There are some math tricks that take years to figure out, but I don't think this one took that long. If I multiply by 1 over x, it's not going to change the output of this function because I'm doing it to both the top and the bottom. I mean, you might wonder what happens when x is 0, because 1 over 0 is undefined. Well, don't worry about it because we're letting x go to plus or minus infinity, not 0. 2 times x times 1 over x is just 2, right? The x's cancel. Minus 5 times 1 over x is minus 5 over x. X times 1 over x is 1. The x's cancel. 3 times 1 over x is 3 over x. Now we can almost plug in infinity. Because what would happen if we, quote unquote, plugged in infinity? 5 over infinity, shouldn't that be 0? And 3 over infinity, shouldn't that be 0? Yes and no. If you did replace those with zeros, you would get the right answer. 2 minus 0 over 1 plus 0 is 2. Oh, we should be a little bit more careful, though. At least one time in class and 1 or 2 times on your homework. We should really be a little bit more official and use a property of limits. The limit of a quotient is the quotient of the limits. Like this. That's a property of limits. That is true as long as the limit on the bottom is non-zero, so I'm not dividing by 0. And in writing this, I'm implicitly assuming it's not 0, and that is correct. It's not, it's 1. I'm not going to be quite that picky about it. I would be okay in this kind of problem if you just write this step like this. Oh, and then we should be a little bit more picky. We should also say that the limit of a difference is the difference of the limits. Oh, this gets to be painful. You don't enjoy it. I don't enjoy it much either, to tell you the truth, but we got to do it. It's part of my job description to do this. I'm serious. But it's kind of funny at the same time. The limit of a difference is the difference of the limits. The limit of a sum is the sum of the limits. These are properties of limits that you'll find in section 1.8. Although in 1.8, they're described in terms of letting x approach a particular number, not plus or minus infinity. But it still ends up being true if it's a plus or minus infinity. More properties of limits. Limit of a constant is the constant. Hey, that's fun. What about these limits? Technically speaking, if we want to be even a little extra picky, the constants that you see should be factored out in front. Oh boy, this is being really extra picky. Hang on, we're almost done. Then these limits are in fact simple enough to declare them to be 0. Those limits exist and equal 0. And so this is the real extra nitpicky way to see the answer is 2. Boy, that's a lot of writing. Do it if you're asked to on 1 or 2 homework or 3 homework problems. It's not the only kind of problem where you need to do this kind of trick. There are some problems also involving rational function ratios of functions that involve like e to the x, where you might have to do something like this. And the trick is to multiply by e to the negative x in that context. Like you've got e to the x. If this x on the top and the bottom were at e to the x in both spots, 2e to the x minus 5 and e to the x plus 3, instead of multiplying by 1 over x on the top and the bottom, you'd multiply by e to the negative x on the top and the bottom. But in the end, it would be a very similar calculation. And it is true, you can take it to the bank, that the limit as x goes to plus infinity of e to the minus x is 0. And the limit as x goes to minus infinity of e to the positive x is also 0. Those are a couple other facts you can take to the bank. We know the graph of e to the negative x looks like this. That's exponential decay. We know the graph of e to the positive x looks like that. That's exponential growth. In both cases, the x-axis is a horizontal asymptote, though only one directional in both cases. We have to do all this on the test. I have put such problems on test before. Sorry. Yes, it's a lot to write. You don't like it, I don't like it, but we need to do it at least once or twice or 3 times to sort of emphasize that there are reasons for things that are a little bit more rigorous than just completely waving your hands. Okay. I'm using properties of limits, which I've not proved, and I'm probably not going to prove, but those limit properties, when we look at them in a little bit more detail, should seem reasonable.